Hello and welcome to MT3. We are still on higher order ordinary differential equations, but once again, the techniques I'm going to be looking at here will be applicable to any order, including first order. So we have seen how to solve first order equations, ordinary differential equations. We have seen looked at general principles which are applicable to differential equations of any order, but now we want to start tackling techniques to solve particular kinds of ordinary differential equations. And the one which we're going to be looking at just two in this tutorial, and then we will see more general techniques later on. So we are now in Riley, Hobson and Ben's chapter 15, specifically chapter 15.1, and now we're dealing with ODEs with constant coefficients. So these are ordinary differential equations of the form a sum I goes from 0 to n of ai. Now instead of ai being functions of x, these are now constants. ai times some derivative of y. Remember the notation y superscript round brackets I means the ith derivative of y with respect to x, under the condition that y superscript naught is simply the function y of x. So here we have the sum going over these derivatives of y equal to f of x. So this is an inhomogeneous equation. If we set f of x to 0, we get a homogeneous equation. Right, so to get the complementary function, we need to solve the homogeneous equation. And that is the sum ai, the I derivative of y with respect to x, and that's equal to 0. So we need to solve this. Now, we're going to solve this equation, this homogeneous equation, using the ansatz, or the kind of starting function or starting value. Y is equal to a times e to the lambda x, where lambda and a are unknown. Now in principle a doesn't really matter, it's a multiplicative constant, we don't care about that. This is the kind of thing which is taken care of when you normalize functions. Alright, it's a lambda that matters here. So we find the ith derivative of this guess y. So y, the ith derivative of y is di y by dxi, and that's simply lambda to the I times y of x. Try it out. Now, if you plug these into the homogeneous equation given here, what you get is the sum I goes from 0 to n of ai, our constants ai, times lambda to the I times the function y of x, and that's equal to 0 for all x. Now, if these functions y of x are not 0, now one second, can they ever be 0? These functions y of x are a times an exponential. Now if a is non-zero, because that would be really the trivial solution, then these, unless lambda was minus infinity, well, the y is never 0. So these functions y are never 0, in which case what we must have is that the sum I goes from 0 to n of the constants ai times lambda to the I, that must be 0. And this is a polynomial equation. It's an nth order polynomial in lambda. This, by the way, is called the auxiliary equation, and it's auxiliary to the differential equation. If you look at its construction, it follows the differential equation in form. The differential equation is I goes from 0 to n, ai, the ith derivative of y is equal to 0, that's the homogeneous equation, and the auxiliary equation is of the same form, except instead of the ith derivative of y, you've got lambda to the I. Now there will be n roots, we know this from algebra, and these roots will be, we'll label them lambda of k. Okay, there are n of these roots. So now we have a few cases. Case 1, all these lambda of k are different. There's a subcase, so 1a. If these lambda of k's are real for all k, then the complementary function yc of x is given by the sum k goes from 1 to n of ck, some constants, times e to the lambda k x, where these lambda k's are the roots of the auxiliary equation. Now, if some of these lambda k's are complex, so if there is, for example, lambda, if lambda, a complex number, is a solution to the polynomial with real coefficients, then we all know that lambda star is also a solution. Now it just follows from the polynomial. The polynomial is given by the sum over ai lambda to the I is equal to 0. ai are real. If ai are real, then you can show, and I'd like you to try it, show that if lambda is a solution, then so is lambda star. So we can group these complex roots in pairs. C1 times e to the lambda x plus C2 times e to the lambda star x. Now if we write lambda is alpha plus I beta, then lambda star is alpha minus I beta, and that lets us perform some simple manipulations on these roots. And I'm not going to bore you with the details, but you can write this down as an exponential of the real part, e to the alpha x, times d1 times a sine term and d2 times a cosine term. Okay, so that's when you have complex roots possible. Now if there is some degeneracy, that means if some of these lambdas are equal to each other, take a specific example. If lambda 1 occurs k times, where k has to be less than or equal to n, then we use as our solutions to the complementary, to the homogeneous equation, as e to the lambda 1x, then x times e to the lambda 1x, x squared times e to the lambda 1x, all the way to x to the power of k minus 1 times e to the lambda 1x. And there are k linearly independent solutions here. You could check it using the Wronskian. In this case, the complementary solution will be given by the sum over these k linearly independent solutions with the same root, so lambda 1, and then the sum over the remainder. Okay, so I will see examples of how this is used, so let's just keep this background in mind while we go on. Now, once you've found the complementary solution, you've got to find a particular solution. Any one will do. And the particular solution is a solution of the inhomogeneous equation given over here, where we now have the function f of x in there. Now, the caveat here is that there are no fail-safe methods for finding the solution, but we have a few approaches which may or may not work. So, number one, if f of x is of the form a times an exponential, where it's an exponential of qx, then try a particular solution of the form b times e to the qx. So we've kept the exponential the same, but we've changed the constant. Similarly, if this source function f is now a1 times sine qx plus a2 times cos qx, try a particular solution of the form b1 sine qx plus b2 cos qx. Now you can see this is related to the first case. Yep. If f is a polynomial, a0 plus a1x plus a2x squared all the way to an x to the n, try a polynomial for the particular solution, but change the coefficients. Keep the order the same, it's both n, but the coefficients are different. And if f of x is any sum or product of the above, then try the particular solution as the sum or product of these guesses too. Right, let's have a look at some examples and see how we put that into practice. The first differential equation is y double prime minus 2y prime plus y is e to the x. So to get the complementary solution, we have to solve the homogeneous equation, which is y double prime minus 2y prime plus y is equal to 0. This is of the form, it's got constant coefficients, so we can use the techniques given above. So we make the ansatz y of x is equal to a times e to the lambda x, which means y prime of x is equal to lambda times y, and y double prime of x is lambda squared times y. You can check these, put them into the homogeneous equation, and we get the auxiliary equation. And if you look at the form, we have simply replaced y, derivatives of y, with powers of lambda everywhere, and that gives you an idea. This is lambda to 0, which is the 0th derivative of y. Solve this auxiliary equation. It's a second order, it's a quadratic equation. We get two roots, and in fact it's a double root. Lambda is equal to 1 is a double root, which means we should now go back to our different cases for the complementary solution. What did we see? Case 2, there is some degeneracy. If there is some degeneracy, then then we will use as independent functions e to the lambda 1x and x times e to the lambda 1x. There are only two in our case. So we try those. Let's go back down. Here we are. So our complementary solution will be some constant c1 times e to the x plus another constant c2 times e to the x. And you can plug this into the homogeneous equation to show that it is in fact a solution. Okay, now we need to find the particular solution. Our source function is e to the x. So we go to our different ways of finding a particular solution. If f is a times e to the qx, then we try b times e to the qx. So that's the first case. So we're going to try a function of the form. We've got a 1 times e to the x. I'm going to use a times e to the x. But this won't work because c1 times e to the x is present in the complementary solution. Okay, fine. So now we try the next power up. X times e to the ax times e to the x, but c2x e to the x is already present in the complementary solution. So we try the next power. We're going to try y is equal to a times x squared e to the x. That's not present over here. Alright, so now we differentiate to find out what a is, and to find out if this is in fact allowed. What we do is we insert it into the inhomogeneous equation. Where is that? That's this equation here. This is the inhomogeneous equation. We insert this function in there, so we need the first derivative given here and the second derivative given here. Put it into the inhomogeneous equation. I've collected terms such that terms with particular powers of x line up, and that makes it much easier to handle when you're doing this sort of thing. And you can see that all these cancel off except for the first, and then that's equal to e to the x, which is the source function. Now we can cancel the e to the x's because it's never 0, so we get an equation for a 2a is equal to 1, or a is equal to a half. So we have our particular solution is a half x squared e to the x. And therefore the general solution to this equation is y of x is equal to the complementary solution, which contains the two constants c1 plus c2x e to the x. And then we have the particular solution, which is a half x squared e to the x, and there are no unknown constants in this part. Here's another example. This is taken from the lecture recording I made on first order ordinary differential equations. To remind you, we were looking at an example of a mass m falling under gravity in an atmosphere. So there was a drag force on it. It was given by minus beta times its velocity. And this led to the differential equation. I won't show you how it was got. Look at those recordings to see. It was led to the differential equation dv by dt is equal plus beta over m times the velocity is equal to g. This is of the form, it has constant coefficients. Now, what we did when we solved this, we used an integrating factor. But here we're going to use this ansatz that the complementary solution is given by a times e to the lambda t. The independent variable is not x, it's time. So that's a lambda times time. We put this into the homogeneous equation. The homogeneous equation is found by setting the source function, which is g, in this case, to be 0. And that gives us the auxiliary equation for lambda. So lambda plus, this is quite simple in this case, there's only one derivative in there. So lambda plus beta over m is 0, or lambda is equal to minus beta over m. So our complementary solution has only one unknown constant a, and it's a times e to the minus beta times time divided by m. What about the particular solution? Well, f of x is equal to g, it's a constant. We're going to try a solution of the form, and v of t, the velocity as a function of time, is another constant, capital B. I hope the beta and the b don't confuse you, but they are two different things here. So you insert this into the differential equation, into this differential equation now, it's the inhomogeneous differential equation, and what you will end up with is 0, because this is equal to a constant, so the first derivative gives us 0. 0 plus beta over m times b is equal to g, and therefore b is equal to mg over beta. So our particular solution is mg over beta, and therefore the general solution is the complementary solution, the one with the constant a, plus the particular solution mg over beta. That was fast, wasn't it? I mean, it's much faster once you've realized what special case of differential equation you've got. These specific methods are faster than those involving an integrating function. So how do we find the unknown constants? Well, for that, you've already seen what happens for first order ODEs. We need boundary conditions. And we're going to see much more of this in subsequent tutorials, so I won't say much more here except to lay down the general principles. Alright, so in general, the solution to an nth order ODE will involve n undetermined constants, and these will be in the complementary solution. These will be the constants we need to find out. And these are determined by n boundary conditions. So they could be of the form y of x1 is b1, y of x2 is b2, etc. They could also involve conditions on the derivatives. So you could have conditions on the first derivative or the second derivative. The conditions on the derivative cannot be equal to the highest. So if it's an nth order ODE, you cannot have conditions on the nth derivative. It has to be the lower derivatives only. Or it could be any combination of these as long as there are n independent conditions. Let's take some examples because that's very general. The kinds of conditions we will see are usually of this form. So for a second order ODE in the range a to b, we may have n point boundary conditions. Y of a is 0, for example, and y of b is 0. That means that the function goes to 0 at both boundaries. These are called homogeneous boundary conditions. Or initial value boundary conditions. It's y of a is 0 and y prime of a is 0. Or final value boundary conditions, where we put these same kinds of conditions but at the end point. Or periodic boundary conditions, y of a is equal to y of b, and the same for the derivative. And there could be others. Now in physical problems, I've noted here, we often see these kinds of boundary conditions, and that's because they often ensure that the operator L we are using is Hermitian, and physical problems tend to use Hermitian operators. So these are the kinds of boundary conditions you're going to be seeing for the most part. Now it can be shown, I want to show you the proof here. The proof is in section 7.28 in Physical Mathematics by Cahill. It can be shown that a second order ODE with homogeneous boundary conditions either has a unique solution or none at all. So if we see boundary conditions of this form, then we know that either there's a unique solution or in fact there are no solutions possible. Alright, so now some other ODEs before we finish this tutorial. Let's take this following example of a differential equation. We have a2, some function a2 of x, second derivative of y with respect to x, plus a1 of x, first derivative of y is equal to 0. So there's no term in a0 in here. Is this second order? Well, it looks second order for sure, but if we put p, which would be a function of x, to be equal to dy by dx, then dp by dx is the second derivative of y with respect to x. So what we can do is write this equation as with p as the dependent variable, and it will be a2 times dp by dx plus a1 times p is equal to 0. Now it's first order in p, and we can solve this using any of the methods we have seen. Once you've got a solution for p, you have to remember that p is equal to dy by dx, so we need to solve for y by integrating this. Alright, I don't have an example here, but keep this in mind. This happens at times, and you can simplify your life considerably by converting the differential equation from a higher order into a lower order. Another example I would like to look at here in some detail is the Euler method, the Euler equation. This is in Riley, Hobson and Benz 15.2.1. So the Euler equation is of the form an constant x to the n and the nth derivative of y, etc., is equal to f of x. So we have powers of x in here, multiplying each of the derivatives. Yeah. And one of the ways of solving this is to change variables from x to, so x, let x equal to e to the t. So x to the n is just e to the n t. And we need to change our variable down here from d by dx to d by dt. I mean, you do it using the chain rule. So dy by dx is equal to dy by dt times dt by dx, which is equal to dy by dt divided by dx by dt. But dx by dt is e to the t. So this becomes e to the minus t dy by dt. Similarly, for the higher order terms, I'm going to leave this here and that you have a look through it. But what you can show quite nicely is that there's a nice pattern here. X times dy by dx is equal to simply dy by dt. We've gotten rid of the x. X squared times dy by dx squared. Likewise, we get rid of the x, and it's the second derivative of y with respect to t minus the first derivative of y with respect to t, and there are no more. And you know, we have gone from something which had a function multiplying the derivative to something which has only constants multiplying the derivative. Or you can write it in this form too. Similarly, for the third derivative, x cubed times d3y by dx cubed is given like this. It's just simply a generalization of this formula. Now what this means is that we can take our Euler equation, which has these powers of x multiplying each derivative, and write it out in a form which has only constants multiplying the derivatives. We'll see how this works. But once you have those, you can then use the technique of constant coefficients, which we've just seen, to solve the transformed Euler equation. Okay? Alternatively, we could use the ansatz y is equal to x to the lambda. And this will lead, as we will see, to an algebraic equation for lambda, which we will solve the way we solve the auxiliary equation to find roots. And here, if there are degeneracies, we will use x to the lambda 1 times the logarithm of x to the lambda 1 times the logarithm of x squared, etc. And here, in this particular example, there's lambda 1 has a k-fold degeneracy, so there are the highest power of the logarithm of x is k minus 1. Let's see how this works. This might all seem a little abstract. Let's see how it works in practice. So here's one of our equations. It is an Euler equation because each derivative of y has got an corresponding x to the n multiplying it. Okay, and so we try it first with the first method, which is x is equal to e to the t. Change variables, and you can show that x times dy by dx is simply dy by dt, and you can also show, using the techniques we've just seen, that x squared times d squared y by dx squared is equal to d squared y by dt squared minus dy by dt. Put these back into the ODE, and it will be transformed from this form to this much simpler form, d squared y by dt squared minus 4y is 0. This now has constant coefficients, therefore we can try y is equal to e to the lambda t. I've dropped the a here because the a is superfluous. This leads to the auxiliary equation for lambda. Lambda squared minus 4 is 0. So lambda is equal to plus or minus 2. Therefore y is equal to c1 e to the 2x, e to the 2 times t. Remember, plus c2 e to the minus 2 t. Right, so we are using this ansatz, sorry. But now we know that x is e to the t. So we can now transform back to x, and this becomes y is equal to c1 x squared plus c2 x to the minus 2. And try it out, put this back into the ODE, and you will find that this is indeed a solution. Alright, what about the second possibility? I said we can also use the ansatz y is equal to x to the lambda. Well, let's try it. So now x times dy by dx is x times lambda x to the lambda minus 1. That's simply lambda times y. And similarly for d squared, so x squared, d squared y by dx squared, we will get this is equal to lambda times lambda minus 1 times y. So the ODE then becomes lambda times lambda minus 1 times y plus lambda y minus 4y is 0. And if the functions y are not 0 except at isolated points, we can divide by y to get an auxiliary equation for lambda. Solve it. Lambda is equal to plus minus 2, and therefore y is equal to c1 times x squared plus c2 times x to the minus 2 as before. Both approaches work. I find the second one easier, but both work. Okay, now there are many more methods of solving second and higher order ODEs. We'll be looking at a few general techniques in the next session, next few recordings. We'll be looking at series solutions of the method of Frobenius, Green's functions. I won't be looking at variation of parameters. It's related to Green's functions, but you can look at this in Riley, Hobson, and Benz if you're interested. And finally, there's numerical solutions using a computer, which is something which I have time. I will put up some recordings on this, but it may not happen. These two are what we're going to be looking at next. All right, so that brings us to the end of this session. We've looked at specific ways of solving higher order ODEs of constant coefficients or equations, or the Euler equation, Euler differential equations, and these will be found in Riley, Hobson, and Benz chapter 15. All right, so we stop here. Thanks for watching.